Assalamu alaikum wa rahmatullahi wa barakatuh. Alhamdulillah wa salatu wa salamu ala rasulillah amma ba'd. So in the previous labs, we have seen how to configure the input and output pins of microcontroller and how to connect a push button and an LED to the microcontroller. So LED and push buttons are digital input and output, and we have seen the port registers and port pins. So the LED and push buttons are LED acts as a digital output and the push button acts as a digital input to the microcontroller. The input signal changes from 0 to 1 or 1 to 0, and the output changes from 0 to 1 or 1 to 0. So in digital signals, you have only two voltage levels, 0 volt or 5 volt. Now let us see, in this lab, we will see how to configure the analog module of the microcontroller. So in this lab and in the coming labs, we will study how to configure the different modules of the microcontroller. So we have timer module, we have capture compare and PWM module, we have the analog to digital converter module. So we will see how to configure these modules of the microcontroller. Now, what are analog signals? So analog signals, they can range from 0 to 5 volt. In contrast with the digital signals can only range between 0 and 5 volt for the microcontroller. So 0 is considered low signal and 5 is considered as the high signal. But in analog signals for the PIC microcontrollers, it can range from 0 to 5 volt. It can be any voltage from 0 to 5 volt. So if we convert the analog signal to its digital equivalent, we need an A to D converter. So PIC microcontrollers, it has its own internal analog to digital converter module. So we can use this module to connect an external signal on the microcontroller pin, analog pins of the microcontroller, and internally it can convert it into its digital equivalent, and we can perform calculations on the digital value, or we can display that as the digital result of the analog input. So where do we find analog signals? So usually the sensors that you find in the market, most of these sensors are analog sensors. For example, the temperature sensor, thermistor, it converts the temperature into a voltage level that you can read as input, as an input to the microcontroller, and you can display that the voltage, the temperature level, or you can calculate and convert that voltage level and display as a temperature on the LCD. Similarly, you have an LDR light sensor. So it detects the amount of light and converts that into electrical signals, and it displays, and you can convert that into, convert that analog input into its digital equivalent and calculate the amount of light and display it on the LCD. Similarly, we have potentiometers. Potentiometers are simply variable resistors. I can change the resistance value, and these potentiometers, they are connected in a voltage divider connection. So the amount of voltage given as input to the microcontroller, the amount of voltage given as input to the microcontroller will depend on the level of the potentiometer. So that is once again an analog signal to the microcontroller. It can range anything from 0 to 5 volt. So this is the example of potentiometer, and you can see this is the example of the thermistor. The temperature sensor, you can find them in two different formats, NTC, which is negative temperature coefficient, and PTC, positive temperature coefficient. So in this case, when the temperature keeps on increasing, the output voltage, it keeps on increasing. As the resistance goes low, as the resistance keeps on decreasing, you can see the voltage here, it keeps on increasing. And in the PTC, if you keep increasing the temperature, the resistance starts increasing, it keeps on increasing, and the output voltage will keep on decreasing. And this is the diagram of the light sensor. So you can find the equation given here under the light sensor. So you will find similar equations given in the data sheet of these sensors. So these equations will help you to convert the output voltage, the analog output voltage, into its equivalent physical parameter, whatever you are measuring. So for example, if you are measuring the light intensity, so using these equations you can convert the output voltage into the intensity of light, and you can display that on the LCD. So this video given in the homework, it shows you a brief explanation of how these sensors work. This example you can find when the temperature starts increasing, a fan is connected to the microcontroller, a DC fan is connected to the microcontroller, and you can see the light and temperature sensor shown here on the LCD screen. And as soon as the temperature increases, the fan starts working here. So this is one example of using analog inputs to the microcontroller. So the steps involved in ADC conversion is sampling and quantization. So you have an analog input, you have to sample the analog input. So for example, at this time you sample the analog input. So let us say the voltage level here is 3 volt. So you have to quantize that input into a discrete level. So 0 0 0 1 1 0 and 1 1, these are the discrete binary levels. So how do you quantize them? How do you quantize the input signal into its discrete or digital equivalent? So that depends on the resolution of your ADC conversion. So in this example, you have a 2-bit ADC resolution. That means each voltage level is assigned with a 2-bit binary digits. So you have 4 levels here from 0 to 5 volt. So that depends on the resolution. So if you have only 2 bits, so you have 4 levels. So what happens is any voltage from 0, so here you have 0 volts. So here you have 0 volt at this level, and at this level you will have 2.5 volt. So similarly, this will be 1.25 volt. So in this case, any voltage, any analog input voltage between 0 to 1.25 will be assigned a value as 0 0, and any voltage level between 1.25 and 2.5 volt will be assigned a value as 0 1. So if you want to increase the resolution, or if you want to be more precise, then you must increase the resolution. So in this example, in the other example here, you have a 3-bit resolution. So you can have 8 levels here. So the number of levels is defined as 2 to the power r, where r is the bits of resolution, number of bits of resolution. So if you have 3 bits, then 2 to the power 3, you get 8 levels here. So you have more precise ADC conversion. So in PIC18 microcontrollers, PIC18 F4580 microcontroller, you have a 10-bit resolution. So there is a simple equation given here for conversion. So it's very easy. For a 10-bit level, 10-bit ADC conversion or 10-bit ADC resolution, the number of levels that you can have is 2 to the power 10, which is 1024 discrete levels. So if you are given any analog input voltage and you have to calculate its digital equivalent, so you can simply cross multiply by using the equation given here. So 5 volt gives you 1024. So an input of 3.65 volt gives you what? So simply cross multiply 3.65 multiplied with 1024 and 5 multiplied with x. So x equals 1024 multiplied with 3.65 and divided by 5. So this 5 is the VDD voltage. So in some of the microcontrollers which run on 3.3 volts, so you have to replace this 5 with 3.3 depending on the VDD voltage of the microcontroller. And 1024 is the number of discrete levels that you have. So in PIC 18F4580 microcontroller, you have 2 to the power 10, that means 1024 levels. But in some other microcontrollers, you may find 8-bit resolution or a 12-bit resolution. So depending on that, you'll have to write the number here. So 2 to the power r. So you can generalize this equation by writing 2 to the power r instead of 1024. So you can write a general equation like this: 2 to the power r multiplied with the input voltage and divided by Vmax of the voltage range. So in some cases you will have a maximum voltage level and a minimum voltage level. So Vmax minus Vmin. So Vmin in our case is 0 volt and Vmax in our case is 5 volt. So you get a 5 volt range here. 2 to the power r is 10 bits here, and Vin is the input voltage. So that will give you the equivalent digital level. So in this example, the digital level is 748, and if you convert this into binary format, you get this number. So you get this number in the binary format. So this is the digital equivalent for 3.65 volt. Now, how to perform all these conversions in PIC microcontroller? So in PIC 18F4580 microcontroller, we have a 10-bit ADC converter module. So if you click on this section number 19 of the data sheet, it will take you to the ADC module, and you can find these registers: AD result high byte, AD result low byte, and AD control 0, AD control 1, and AD control 2. These are the registers. Using them, you can configure the ADC module. So before we start using the ADC module, first we have to identify where we connect our analog sensors. So if you look at the pin diagram, you'll find some of the pins, they are multiplexed as AN pins, analog channel pins. So you have AN0, AN1, AN2, AN3. Here you have AN10, AN8. Okay, so first we have to identify which of these pins we are going to use for our analog input. So depending on that, we will choose or we will configure those pins as analog pins and the remaining pins as digital pins. So let us say if you are connecting an analog sensor on pin number 3, which is RA1 or AN1 pin. So if you connect your sensor on this pin and you want the remaining pins to be as digital pins, for example, if you want RA2 and RA3 to be digital pins, so how do we configure that? So first we will start using configuring the AD control 1 register. So we'll start with this register first. So in this register, you find these are the 6 bits which are implemented, and among these 6 bits, these 4 bits, the last 4 bits, they are arranged as a table here. So you find the analog channels given here at the top, AN0 to AN10, and in the table you can find diagonally half of the table is filled with D and half of the table is filled with A. So A for analog input and D for digital input. So if you want to configure AN1 as analog, then we choose this option here. So in this option, we have AN1 as analog and the remaining pins as digital. So we can use these digital pins for any digital input or output. And this pin becomes an analog pin, and along with that, the AN0 pin also becomes an analog pin. So we will choose this option and we'll copy this number 1101 to these 4 bits 1101, these 4 bits of this register. So that will configure the analog input, or that will configure the pin as an analog pin or a digital pin. And if we have multiple analog inputs, so depending on how many inputs we have, on which pins they are connected, we choose that many pins as analog pins. So suppose you have AN1 connected to the light sensor and AN3 connected to the temperature sensor. So we look at this line here, this option here. Here we have AN3 as analog and AN1 as analog. Both of them are analog. So we choose this option and we'll copy 1011 to this register, or these bits of this register. Okay. So once this is configured, those pins will be configured as analog pins and the remaining pins will be configured as digital pins. And these 2 bits here, they are used to select the reference voltage for ADC conversion. So normally ADC conversion can take place between the VSS, which is ground, and VDD, which is 5 volt. But if you want to change the range of ADC conversion, so instead of converting from 0 volt, if you want, let us say that your analog sensor gives you an output between 1 volt to 4.5 volt only, so it does not give you anything less than 1 volt. So what we can do is we can connect this pin, V reference negative pin minus this pin. We can connect this pin of the microcontroller to a fixed DC voltage supply at 1 volt, and we can connect the V reference plus pin, the positive pin, to a fixed DC voltage supply at 4.5 volt. And in that case, you'll have to configure these 2 bits as 1 and 1. So if you are using them, you have to configure these as 1. So these 2 pins will be connected to the lower and higher reference voltages. Now what will happen is the ADC conversion will only range between these 2 values. So any voltage level below V reference minus will give you 0, and any voltage level beyond or greater than V reference plus will give you all ones. So this is for the voltage reference selection bits. Then the next part here to configure is the AD control to register. So analog to digital converter, control register 2. So in this register we have 3 things to configure. We have the ADC conversion clock selection bit. So ADC conversion cannot take place at the same speed as the clock frequency of the microcontroller. So it has to be at some lower frequency or lower speed. So we can choose one of the options given here. So oscillator frequency divided by 64 divided by 16 divided by 4, or FRC. FRC means the clock of ADC is derived from or generated by the RC oscillator inside the ADC module itself. So ADC module, once again, it also has an RC oscillator which can generate its own clock frequency, and that can be used as the clock frequency for the ADC conversion. So we can choose this option FRC from here. So this is one selection here, and the second selection is the AD acquisition time selection bits. So this time, the acquisition time, is also known as the sampling time. So when you sample an analog input, there will be a charge holding capacitor at the input level like this one. So the input capacitor, it has to charge and it has to keep the level, or it has to keep the analog input level constant throughout the ADC conversion, because the analog conversion, ADC conversion, is not instantaneous. It takes some time. So you have to, it has to keep the input level constant during the whole conversion process. So you have the ADC module has to wait for the capacitor to charge and to hold the voltage level. So we can choose from these options how much time the microcontroller should wait before it starts ADC conversion. So we can choose one of these options given here: 2 TAD, 4 TAD, 6 TAD. Now TAD is the time taken for 1 bit ADC conversion. So in this microcontroller we have 10 bit ADC conversion. So what is the time taken for 1 bit conversion? That is 1 TAD. So we can choose the options given here. So this is the timing diagram which shows you the ADC conversion. Before the conversion starts, depending on the TAD selection, it will wait for that many TAD cycles. So for example, in this example you have 4 TAD, so it is waiting for 4 cycles before it starts the ADC conversion. And because we have 10 bit ADC conversion, it takes 10 TAD cycles for conversion and another extra cycle for storing the result. The clock frequency, ADC clock frequency should be between 1 microsecond and 6 microsecond. It should not be too fast, it should not be too slow. So if it is too fast, then the conversion will not be accurate, and if it is too slow, then you may find that the input charge holding capacitor starts discharging, or the input voltage level it starts changing, so we will not get an appropriate or the correct result. So in this table you find some of these cells, they are shaded cells, and some of these are non-shaded cells. So you can only choose the values given here in the non-shaded cells. So if the clock frequency is 8 megahertz, then you can either choose this one, FOSC divided by 16 for the clock frequency, or FOSC divided by 32, this one, or FRC. So divided by 16 gives you 2 microsecond, divided by 32 gives you 4 microsecond, or we can choose FRC. So in this option, the clock is generated by the ADC module itself, so it will range between 2 to 6 microseconds. Then the last bit here, the MSB of AD control 2 register is the ADFM bit. ADFM bit is the AD result format selection bit. So since we have 10-bit ADC resolution, the result of ADC will be a 10-bit result. So 10 bits cannot be stored in an 8-bit register. So data memory of PIC microcontroller or PIC18 microcontroller is only 8-bit wide. So how do you store a 10-bit result? So for this we have two registers here, AD result low byte and AD result high byte. So you can store 10 bits in these two registers as either right justified result or a left justified result. So in the right justified you have lower 8 bits here and the higher 2 bits here, and the left justified you have higher 8 bits here and the lower 2 bits here. So both these options, they have their own application. So in some of the cases you want to use only the 8 bits of the ADC result. For example, if you want to show the ADC result on a port, a digital port of a microcontroller, for example port C or port D. So port C or port D, they are only 8-bit ports. So you cannot show a 10-bit result on those 8-bit ports. So what we can do is we can scale down the ADC result, and instead of showing all the 10 bits, we can choose left justified result and display only the higher 8 bits of the ADC result, and we can ignore the LSBs, which is the low significant bits or least significant bits. So in this case what we are doing is we are simply decreasing the resolution from 10-bit result to an 8-bit result. So this is for choosing only an 8-bit result and displaying it on any port or any other calculation. But if you want to choose, or if you want to display the 10-bit, or if you want to use 10 bits together and use them for any calculation, then in that case you must choose a right justified result. So in that case we'll choose right justified result, and we'll have to use both these registers together, the AD result low byte and the AD result high byte. You'll have to use them together to use the 10-bit ADC result, and you can use it for any calculation. So in this register we have seen the ADC clock frequency, the number of TAD cycles, and the AD result format selection. And in the previous register we have seen configuration of the analog channel input pins, either in analog or digital format, and the selection of the voltage reference levels, low and high voltage reference levels for the ADC conversion. Now the next register is the AD control 0 register. So in this register, we select the analog channel from which we have to start the ADC conversion, and there is a go bit to start ADC conversion. This bit, when it is set, it will start ADC conversion, and when the conversion is completed, this bit automatically it becomes 0 to indicate that the conversion is completed. And AD on bit is to enable the ADC module. So without enabling ADC module, you cannot start an ADC conversion. So previously we have seen in the AD control 1 register. In the AD control 1 register, we select or we configure the pins, the input pins or the analog channel pins into either analog mode or digital mode. So we might have multiple analog sensors connected on different analog pins. So in this register, so AD control 1 register is used to configure the pins in analog mode or digital mode. And when you actually start your ADC conversion, when you are actually starting your ADC conversion, we have to select the analog channel from where you are taking analog input, or from where you are sampling analog input. So for example, we first choose AN channel 1, AN1, and then we set the go bit to start ADC conversion. When the conversion is completed, we copy the result, and then we move on to another channel, for example AN5, for example, and then we start ADC conversion once again for the next channel, and then when the conversion is completed, we can disable the ADC module, or we can repeat the process once again. So there are example code snippets given under each ADC control register. So for example, to configure the AD control 0 register for analog channel 0 in 0, we have to copy 0000 in all these bits. So all these bits are 0. So whenever you write a assembly code and you come across a new register or new SFR, you can copy the name of the register along with the bits of this register as comment inside your program code, and in the next line you can write the data bits under these bit names, so that when you look at this, you can easily understand why you are copying this data in this register. So since we are selecting here in this example, you are selecting N0 as the analog channel, so these bits are all zeros, okay, and the go bit will remain 0. We do not start the conversion in the same step where we configure the ADC module. So we configure the ADC module in one step, and in the next step later on we start our ADC conversion. So AD on bit is 1, so that means we enable the ADC module. Go bit is still 0. We do not start ADC conversion, and we select the analog channel here. Okay. The next register, AD control 1 register, it is 0E. That means we have selected here 1110. That means we have selected AN0 as analog and the remaining pins as digital here in this example. And these two reference selection bits are still 0. That means we are using VSS and VDD as the lower and higher voltage reference. Similarly, in the AD control 2 register, the example given here is 17. That means the ADC clock is 111, which is FRC clock. Okay. Then the acquisition time is 010, which is 40 AD, and ADFM bit is 0. That means we have selected left justified result. So always we choose left justified result whenever we want to use only the higher 8 bits of the ADC result and we want to ignore the LSBs. So we choose left justified result in this case. But if you want to use 10 bits completely and we want to use it in any calculation, so in that case, we always choose the right justified result, and we have to use both these registers together. So in the left justified, we can discard the lower 2 bits and we can simply use the AD result high byte. But in the right justified, you cannot discard these 2 bits because these 2 bits are the MSBs. MSBs means most significant bits. So significant bits, you cannot discard them. The least significant, you can discard them because these are the least significant bits. So we are choosing here in this example left justified result, okay, with 40 AD and FRC ADC clock. So after all this configuration, we will start our loop, the program loop for starting ADC conversion. So you can find the steps given here to configure the ADC module, configure analog pins, voltage reference pins, and digital input and output pins using the TRIS register for configuring the input and output, and the AD control 1 register for selecting the analog and digital pins. Then select the ADC input channel using AD control 0. Select the ADC acquisition time in AD control 2 register, the conversion clock again in AD control 2 register, and the left and right justified again in the same register. And later on we switch on or turn on the ADC module. Then wait for the required acquisition time if it is required, and then start ADC conversion by setting go bit. So as soon as you set this go bit, ADC conversion will start taking place, and when the conversion is completed, this go bit becomes 0. So you have to keep on checking this bit by using a loop. So as the example given here, BSF AD control 0, go. That means this go bit is 1. It has started conversion, and then bit test file register skip if clear AD control 0, 1. So it is waiting and go to $-2. That means it goes back to the previous instruction, and it keeps on in this loop. It keeps on executing this loop and keeps on checking bit number 1, which is go bit of AD control 0 register, until that bit becomes 0. So when it becomes 0, it will skip if clear. So it will skip here, it comes here. Now when the conversion is completed, where is the ADC result? As we know, the ADC result is stored in these 2 registers, AD result high byte and AD result low byte. Since we are using only 8 bits with left justified result, we are using only the higher 8 bits. So we don't have to use the AD result low byte. We can simply copy AD result high byte to an output port, for example here latch B. So whatever ADC result has taken place, that will be displayed on the LEDs connected on latch B. So this is an example, and in the activity you have these 2 sensors connected, the temperature sensor and the light sensor. They are connected to AN1, LDR connected on AN1, and thermistor connected on AN3. So you'll have to configure AN1 and AN3 as analog using the AD control 1 register. That means when you configure that, AN3, 2, 1, and 0, all these will be configured as analog pins, and the remaining pins you can configure them as digital pins. Then configure 40 AD with FRC clock and left justified result in AD control 2 register, same as what is given in the example. And in the AD control 0 register, you have to first start conversion from one of these sensors. You cannot, ADC conversion cannot take place simultaneously for both the analog channels. So it has to be in sequence, one after other. So first select AN1 as the analog channel in AD control 0 register. Then start your ADC conversion. When the conversion is completed, copy the result and display that on port B. So you can copy that result to latch B, and it will be displayed here on these LEDs. And then change the channel in the AD control 0 register, change the channel to AN3. Once again, start the conversion, and when the conversion is completed, display the result on port C. So it will be displayed here on the register, on the LEDs connected on port C. In MPASM, you can write the name of the bit here, BSF AD control 0, go. But in the new assembler, in the PIC-AS assembler, it does not recognize the name of the bit like this. So write the location of the bit number here as 1, which is location of the go bit. So you can see the example working here in the simulation. So this is the simulation that you have to complete for this activity. So we have LDR connected on AN1 and thermistor connected on AN3. LDR sample, analog sample of AN1 is converted and displayed as digital format here on port B. So we can use these buttons to increase the voltage here. So as you see, the input voltage here from the LDR is 1.4 volts at the moment, and we can increase the temperature here. So as you see, the numbers displayed here on port B, they keep on increasing. Okay, so this is for the LDR, and similarly the thermistor is currently 2 volt and it is displayed here on port C. So once again, if you keep on increasing, so now it is 3 volts, 4 and 5. So this is jumping with 1 volt level, and the LDR is has more resolution. It keeps on increasing with minor levels, small voltage levels, and you can see the difference here. You can see the difference in the output here. So since we have connected RB0 here on the top and RB7 in the bottom, so the MSB is here, the most significant bit is here, and the least significant bit is here. Same way, RC0 here is on the top and RC7 is at the bottom. So you can see the numbers displayed here on the LEDs. So complete this activity in MPLAB. Call the delay loop in your in the main loop of the program. So first you'll have to set the trace registers for input and output. Then after that, configure the AD control 0, 1 and 2 registers. And then this is a sample of this is an example of the first conversion. So we are selecting in channel 1 here. So 0001, which is channel 1, and go bit is still 0 and AD on bit is 1. So we copy this data in AD control 0 register. That means the in channel 1 is selected. Then BSF AD control 0, 1 start ADC conversion, and when the conversion is completed, so this is the loop for the conversion. So it waits for the conversion to complete. When the conversion is completed, we are copying the result to latch B. Similarly, you'll have to repeat similar instructions for the other sensor connected on AN3 channel. So this is all for this lab. Complete the activity, and you have the explanation for analog channel given in your homework as well. So this homework link which is given to you, it explains to you the working of analog modules of PIC microcontroller. So read this chapter to understand the working of ADC modules, and you will find that this is related to PIC16 microcontroller. The concept is same, but you will find slight differences in the name of the registers or the name of the bits inside the register. But the concept for ADC conversion and how it is configured in ADC in the PIC microcontroller, it is same. So read this, read all about this, and it will help you understand this lab and complete the lab. Complete the lab and submit the activity on Blackboard. And if you have any doubts, you can post them on the discussion forum on Blackboard. So that's all for this lab. Assalamu alaikum wa rahmatullahi wa barakatuh. Subhanallah wa bihamdihi, subhanakallahumma wa bihamdika, ashhadu an la ilaha illa anta, astaghfiruka wa atubu ilayk.